Hello, thanks for watching this second screencast on the KL Divergence. Hopefully you've watched the first one, Understanding Entropy, because I'll be referring to that. So first of all, a little bit of notation. PI, BI will be the same. QI will be what we think the probability of the ith symbol is, where the actual probability is PI, okay? And so then based on this these incorrectly assumed probabilities, we're going to come up with how many bits we use, which will be negative log of qi. So the question is, given that we have these incorrect beliefs and therefore we use the wrong number of bits, what is the expected cost of having the incorrect belief about the probabilities? Because sometimes we'll use too many or too few bits. And the answer is quite simple. So we found the minimum of this, and we found that qi should be equal to pi to minimize this. So the cost is just going to be the cost when we have the wrong value of qi. Whoops. Oh. The cost is going to be this minus the sum over I of minus pi log of pi. Right? And we can combine this into one term, which will just be the sum over I of pi times the log of pi over qi. Okay? And so, apart from the derivation, I don't think it's obvious that this is definitely going to be a positive quantity, but it will tend to be a positive quantity. Because we're taking something bigger minus something smaller, because that's the minimum. So yeah. So what are some properties of the KL divergence? Well, first of all, it's asymmetric. We've got pi over qi, and then we've got a pi here, right? So if qi was the correct probability and pi was the incorrect one we were assuming, we would get a different number. However, it can be used as a measure of how different two probability distributions are. Now, it's not symmetric, so it doesn't have some nice properties that we like to have when measuring the distance between two things. So we can't define a metric space using the KL divergence. However, it does give us some notion of the distance between two probability distributions. And finally, it also has a continuous version, because we don't always have discrete things. And so I want to talk a little bit more about the continuous version. So let's talk about entropy first. So entropy is equal to the sum over I of pi log pi with a negative. And so the smaller pi gets, the bigger in size, right? The bigger this part gets. And so if you have a continuous distribution, then, well, the probability of being at any certain point is 0, right? So this is going to negative infinity times a negative gives you positive infinity. And so you can think the entropy would be infinite if we measured it using the standard formula. So, however, we would still say that, well, this has maybe less entropy than this, right? Because this probability is much more spread out. And so we're going to introduce, using integrals, a version of the entropy that works for the continuous case, which captures this notion that being more spread out in terms of distance now means more entropy. So this was the discrete version, and then we'll do a continuous version. And so it's just going to be the analog of this, except we're going to do the integral over whatever the range is of the probability will be replaced with the density function. So fi of x, say, log fi of x with a negative still. Now, yeah, so that'll be the kind of continuous version of the entropy. Note that as, let me see, you could have continuous functions approximating a discrete one, right, becoming closer and closer, but this would not get closer and closer to this. This would actually approach negative infinity. So they're not the same formula. This is a version that basically works for the continuous case, and this has a notion of distance. Whereas here, this doesn't have a notion of distance. So then we can talk about the KL divergence, a continuous version of that. Which will be defined analogously. We'll just replace this with, maybe I'll say FP to denote, for the correct probabilities, it's the density function of x log of fp of x over fq of x. And there we go. That's the continuous version of that. All right, so just to review quickly, basically to find the extra cost of having an incorrect belief and therefore using the wrong number of bits, we just take the difference between these two, which gives us this, and that's what the KL divergence is. And the KL divergence is a kind of measure of the distance between two probabilities. However, it is asymmetric. So the distance from P to Q and the distance from Q to P would be different. So not the standard. It doesn't have some of the properties that we like distance metrics to have. And we can also define a continuous version using integrals, which is what the paper on the arrow algorithm uses to measure the distance between two Gaussians. All right, thanks for watching.